van der Pol system. In this exercise, we'll study the system which is described by a differential equation, a second-order differential equation which is nonlinear and given by this equation, where y is a function to be found. The first question is to formulate with a state space representation, where the state vector is y dot, and then we'll have to give the state equation of the system. So for this, we consider here, we take x as a state vector, which corresponds to x1, x2, but x1 as given here corresponds to y, and x2 corresponds to y dot. So to have a state formulation, we should have something of the form x dot equal f of x. So for this, I will have to reformulate this state equation, this differential equation. So y dot corresponds to x2 dot. So to have this, I will rewrite as follows: x dot 1 equal x dot 2 equal, and here I am only allowed to have x1 and x2. So x dot 1, which is here, corresponds to, since x1 corresponds to y, x dot 1 corresponds to y dot, which corresponds to x2. Okay. Now x dot 2 corresponds to y dot dot, which corresponds here to, so y dot dot corresponds to minus y dot minus 1 times y dot minus y. Now this one corresponds to this to x1 square. This one corresponds to x2, and this one to x1. As a consequence, here I will write, since this one corresponds to x dot 2, here I will have minus x1 square minus 1 times x2 here minus x1. So recall that here I am only allowed to have x1, x2, but I am not allowed to have the derivative or to have some y's somewhere. So this corresponds to a state formulation of the van der Pol system. Now, second question, we have to linearize this system around the equilibrium to study the stability. So we have to find the pole of the system and to check if it is stable or not around the equilibrium point. That's what I will do now. So the second question. I will rewrite, so I will consider this equation, and this corresponds to the evolution function, which is f of x. Recall that I have x dot equal f of x, where x equal x1, x2. Okay. So now, to find the equilibrium point, I should have x dot equals 0. So it means that I should solve f of x equals 0. It is what I will do now. I will solve f of x equals 0 to find the equilibrium point. So for this, I will have x2 equals 0 due to this. And now, since x2 equals 0, I will have minus x1 due to this equals 0. So it means that the only equilibrium point is x, let's say bar, equal 0, 0. So if I want to linearize, I will have to linearize near to an equilibrium point, just to study the stability. So for this, I will rewrite the I will linearize. So what happened is that around 0, so x1 square here is almost equal to 0, and it means that I will rewrite those f of x is approximately equal around 0 to x2, so x2 which is here minus x2 due to this, since this one is almost equal to 0, minus, excuse me, here it's a plus, minus x1. Okay. So in a matrix form, I will have x dot almost equal around 0 to 0, 1, minus 1, ones times x. This corresponds to the evolution matrix A, and we know that the eigenvalues of A will give me some information about the stability. So for this, I will compute, to compute the eigenvalues, I will compute the polynomial, characteristic polynomial P of S of this matrix. So it corresponds to S times identity, where S is a Laplace variable, minus A. And I take the determinant of this. So I will have the determinant of SS. This one corresponds to S times identity, minus A, 0, 1, minus 1, 1. Okay. So this is equal to the determinant of S minus 1, here 1, and here S minus 1. Okay. Which is equal to S multiplied by S minus 1 plus 1, which is equal to S squared minus S plus 1. So this is the characteristic polynomial of my matrix A. From this, I will have to solve P of S equals 0 to find the eigenvalues of A. And if I do this, I will obtain two eigenvalues, lambda 1 and lambda 2, which is equal to R to these values, and lambda 2, the other eigenvalues, is the same with a minus. So in the plane, in the complex plane, so here it's I and here it's 1, the eigenvalues lambda1 and lambda2 are something like here and here. They are conjugate, of course, since the coefficients of the polynomial are real. So since they are on the right part of the complex plane, it is unstable. So moreover, those who the complex part, they are unstable, but also they will correspond to some oscillation. So it means that the corresponding solution with respect to time in a linear point of view will be something like unstable, like this, and it will oscillate. And the envelope will be something like an exponential corresponding to exponential of t divided by 2 due to this. Okay, so I have proved the instability around 0, and now I will switch to the third question. The vector field is now represented here and will initialize the system around 0, and then from this picture I will try to draw the solution x of t of the nonlinear system. For the question number 3, recall that I have my state equation here of the form x dot equal f of x, and here it is a vector field x1, x2. This vector field corresponds to this function. So how can I draw it? I take a gridding with many points, for instance this point, this point, this point, and so on. So many points like this. And for each of these points, let's say this one, I will compute f of x, and it will give me a two-dimensional vector. Then I draw this vector, but often this vector is big, like this. There is no reason to be small, so there is some kind of normalization, and I draw it so that the arrows will not cross like this. Okay. So this is done by mesh grid and quiver in Python, in MATLAB also, or other languages. So if I, for instance, if I switch to Python, I will have a draw field which is inside the autolib library available here. If I have a look to autolib, I can see that I use in Python the arrange to make the gridding mx and my. Then I will compute the corresponding grid from these two vectors. I will compute f, which is given, the function which is given as an argument here. I will normalize all of them, and quiver will draw the field. So if I run the this one which calls draw field and send f, given here corresponding to the evolution function of the van der Pol function, if I draw it, I will obtain this, and we can see here that all the rows have exactly the same size, which is quite comfortable if we have a better view of the limit cycle and so on. But sometimes we do not ask to have the normalization to see where I go fast or where I go slow. It was the case here where the normalization is not done. You can see that we have longer rows and very small where I go slowly. Okay, so now if I start here, my initial point is taken as x0 equal 0.1, 0. So it means that it is here. If I draw here, okay, so if I follow the vector field, I will do something like this, and I will converge to a limit cycle corresponding to the van der Pol limit cycle. So what I do with the pen corresponds to an integration chain, and usually we use Euler method or Wunsch-Gutta method, depending if I want to be precise or not, depending on the system. So if I do this, a trajectory is given here. Okay, and from the initial point, and now what I want is to have the solution for y. Y corresponds in the exercise, y corresponds to x1. So if I'm now interested in only x1, I can see that if I follow this one with respect to time, at time t equal to 0, I'm here, and I will move left like this. Once I'm here, I will move right and left, so now I'm here, left and right and so on. So I will do something like this. And if I draw with respect to time, we can understand that I will obtain something like this. Okay, so I will try to explain. So if I start here, we can see that x1 corresponding to y is small, 0, almost 0. Then I move right, so I increase here. I will move left here, and then I will move right up to here, and left up to here, and so on. This is why I will obtain some oscillation like this, and this is why the van der Pol equation is called an oscillator. To understand why I have an oscillator from the initial differential equation, I should remember that if I have something like this, a linear equation like this, equals 0. So this linear equation corresponds to a typical mass spring system like this, where 0 is the equilibrium position. This one corresponds to the friction. So if I have no friction, then the mass, this one corresponds to y. If I have no friction, so alpha equals 0, I will oscillate like this, and the solution will be a sine. So it corresponds to alpha equals 0. If alpha is positive, so it means that I have some friction, but I may have something like this. So alpha is positive, the friction is positive. If the friction is negative, then I will have something like this, unstable. So alpha is negative. So what happened in our situation is alpha is this coefficient. where y is big, then the friction becomes positive and the energy will be taken from the system. And when this one y is too small, then alpha will become negative and some energy will be given to the system. This is why I can understand that I will have some kind of stability around the limit cycle. So the limit cycle we have seen here is stable, and it means that it will not be very sensitive with respect to the integration chain. That is our last question. We have to simulate the system with an Euler method, but also with a Runge-Kutta method, and we'll see that when we compare both integration chains, the result will be equivalent. So to perform a simulation, I will consider first my function f, which corresponds to the van der Pol system, and this vector has two inputs and return two outputs, so it corresponds in Python to what we call a tuple. It's not a vector. This is why I made, and it is necessary to have this to be able to draw the field here. Okay, we need a function f which takes as an input real numbers and return real numbers, so floating point numbers, so that we can use mesh grid operators. Now, for using Euler method, we'll prefer to have to transform to use x as array. So in Python, to represent array like this, we need a vector array, which is given in numpy, where here I will have, for instance, x1, x2, and here I put also brackets to say, and this will give me x1, x2. Okay. So fa, like array, we take as an input a vector or an array, and will return an array here. And then I will be able to use two different integration chain to integrate x dot equal f of x. The first one is the Euler method, which tells me that x at time t plus dt is approximately equal to x of t plus dt times f of x of t. This one is quite intuitive, since if I'm here at point x, this corresponds to x dot, and it corresponds to the speed of the state. We can understand that if I'm here at time t plus dt, I will be here, and this one plays the role of the speed. The Runge-Kutta method is different. Here we'll have, with the Runge-Kutta method, we'll have here x at time t plus dt is approximately equal to x of t plus, so here, some kind of speed. But the speed is not taken only at time x. I will integrate, so here it's x. I will integrate, and I make a guess that probably I will be here. But once I will be here, it's a Euler estimation, then the vector field will be like this. So probably in the trajectory, I will have some kind of average between what happened at time t and what happened in the near future. So the vector field will not be like this, but some kind of like this. Mixture between these arrows and these arrows, an average. And it is exactly what is computed here. I have some average between f at time x and f later. So this corresponds to the Runge-Kutta method, which is much more accurate. So I will not enter into mathematical detail, but the order of convergence is local and global convergence will be smaller, okay, or the order larger. Sorry. So now what happened is that I will initialize XR are like Runge-Kutta and here like Euler at the same initial condition, just to make the comparison. I will perform an Euler integration scheme and here a Runge-Kutta. Runge-Kutta, Euler, given here. And then I will draw a point, red for Euler and blue for Runge-Kutta. I switch to Python, I run, and I can see that at the beginning the blue and red are almost okay. So the red is outside the blue, but since I converge, you will see here there is a big difference. But since I have a limit cycle which is stable, the perturbation between the two integration schemes will disappear and both will converge to the stable limit cycle. But there is a difference with respect to time, but the behavior of the oscillator is almost the same. So we can continue like this. We'll observe that both will converge to the limit cycle. So it means that when the system is structurally stable, so when it is stable or when the limit cycle is stable, the behavior of the different integration scheme are almost similar, and it is exactly what happened in robotics or when we have control systems. So we are not very sensitive to the control, to the integration scheme. Now, when we want to predict planets motion or that are not controlled, that are not so stable structurally, it means that when we modify some initial condition, then the influence later will be large, and since we want to predict exactly where are the planets, for instance, we need to perform integration chains that are accurate. This is why in this context it's better to use the Runge-Kutta method and not to use the Euler method.